The next conversation is going to be from Maggie Bump from NanoSonic, and she'll tell us about how termites build. And so it's a very interesting concept and a lot to learn here. Thanks, Maggie.
Thank you. All right. I would like to thank Tricia and Carol and John for organizing. This has been great. Let's see. Oh, if I can move forward. All right. So as Chris said, I am Maggie Bump. I'm coming from NanoSonics, so we're a company in southwestern Virginia. We're in the mountains there near Virginia Tech. And today I will be talking about some termite bioengineering and how we might use it at disaster site recovery. So I'll start with some background on NanoSonic. We are a small R&D group that works a lot in materials. Then we'll talk about cement and how that's gone for us, what we found so far, and then where we want to go from here, what we think we can do with it. So my background is in organic polymer chemistry. There will only be one slide that actually has structures on it, so don't worry about that. But I started off doing polymer synthesis, so that was my graduate work. And that was in the 90s. So growing up in the 80s, going to school in the 90s, the big concern was getting trash into the landfill, right? We had concerns. We knew that it was being dumped in different places, and we wanted to bring it all together. But in polymer chemistry and doing synthesis, we were making great materials. We were solving problems, and it was exciting time, and we were going to make all of our stuff better, all right? And so I've been teaching at Virginia Tech. There I am. And while kind of pursuing this idea of sustainability, because I've always been interested in that, I was able to write lesson modules for the Green Chemistry Institute, develop a class on trash, so what happens to our stuff after we get done using it. And the students that were coming in and taking that class have a different perspective, right? They grew up in the aughts and the teens, and there's now jars of trash in the ocean. There's now straws in sea turtles. And so plastic is a bad guy, all right? So the stuff that I've been making for 30 years, now has to be rethought about. So in working through that class, what I've realized is our relationship to our man-made materials has shifted over the past several decades. And so now we've got this concern over how are we going to kind of undo what we've done. So I'm seeing it in the students that are coming in. They were taking that trash class because they wanted to know, what are we going to do with the stuff after we're done with it? I was at a polymer conference at the beginning of the month, and what has changed over the decades is now the showcase of those talks was how we're going to recycle the stuff that we already have out there, and how we're going to design new materials that will fit into a circular economy. Can we work with biosourced starting materials? Can we develop biodegradable polymer systems? Can we incorporate a piece in there that will let it click apart so we can run it back through the cycle? How do we recover this stuff? And the other place that sustainability has led me is to this company, NanoSonic. So I've been with NanoSonic for a couple years, and one project that I'm working on is, here I am in a hemp field down in North Carolina, because I'm looking at using enzymes and using enzymes to do a degumming of hemp fiber, right? So instead of taking the chemical route, can we follow nature's example, and can we make this process greener? Now, what I will be focusing on today is, here, we're going to talk about the termites. And when you think about the termite mound, all right, there are people that for hundreds of years have already known how amazing it was, right? So in African countries, they're cutting these things up, they're using them as bricks. And so what we are looking at with the USDA is a concrete, and the question is, well, what can we learn from what we have around us? So NanoSonic, here's our current building. So we've got 30,000 square feet, a lot of materials work that's going on there. We can take our small reactions, we can do them in the lab on a small scale, and if they've got interesting properties, we have the capacity to scale up to like a pilot size. We're not doing large scale production, but we can get more material. And then we have advanced manufacturing techniques that will let us try out new ideas and new patterns and techniques there. So we have several products that have been developed over the years through SBIR, so that Small Business Innovation and Research Grant. What I have come to love about that is in looking at the solicitations that the federal agencies are putting out there, you get a snapshot of what they're interested in. So if we're trying to move biomimicry into the mainstream, if we can find a fit up here, there's money behind it. And so now we've got a market. So that's one thing that we'll kind of think about. And I see this more as a timeline. This actually came from one of the students that took my trash class, but this, oh, the pointer, it's throwing me off. This was me growing up, all right? We had a nice linear economy, and yeah, we had waste, and we were gonna put it in one place, and we were gonna take care of, whatever was draining out the bottom of it, but that was gonna work out for us. And then we started shifting to, well, in the 90s, we have a lot of plastic. We should recycle that stuff. So let's sell it. We're going to recycle it, and everybody's going to buy in. And we did, and we recycle about 10% of it. So that one didn't really take care of this at all. And now population has gone up, and our consumption has gone up. And so now we've really got to move towards this idea of that circular economy. How do we keep track of this? How do we design something where we're tracking that end life? And it's not an end life. It rolls right back into the cycle. So let's look to nature, right? Because nature is the master of the circular economy, right? There is no waste in nature. Again, another slide from a student that was in the class. And if we think about the principles of that circular economy, right? We want to use our materials, but then we want to make sure that we don't lose the value over the course of it. And when we get to the end of life, it shouldn't be going in the waste. It should be finding another purpose and another use. And so when we look to nature, that's where we can start to get some ideas and guidance, and you all know this. So what I want to do then is talk about what we've got at NanoSonic and what we're looking at as far as trying to promote this sustainability and how we are trying to move some things around. So what we have here, all right, this is a small-scale 3D ceramic printer that we have, so we can 3D print ceramics and concretes. If we think about 3D printing as a mode of manufacturing, we can do intricate details, all right? So there's a lot of exciting work that's going on in 3D printing to get the structures that you want. So now we can go a little more intricate than we could before. If we think in terms of Portland cement, right, what we see here is an increase, and then we've got about 4 billion metric tons. So concrete, you've put the aggregate in there. The construction or the preparation of the Portland cement has a lot of CO2 produced with it. So for about every ton of that cement that's being made, you're getting close to a ton of CO2. So what we are doing is taking a look at a different cement, geopolymer concrete. And then what we want to do with it is 3D print a house. And the aggregate we want to use is on site. So if we can take the building when disaster has struck, and now we can use that rubble as the aggregate in our cement, now we don't have to transport. So if we can cut down on transport, we can save on CO2 production. This is a 3D printer, so there are a couple places here in the U.S. that are now working with Black Buffalo's gantry printers, and so you can gradually print up your wall. This is a house that it was built in Williamsburg, Virginia, with that 3D printing. If you look at the edge, you can actually see the layers as they go up on that. So what we're doing is we're taking industrial waste, ash and slag, and we're combining that together to make the cement. So if we think about trying to make a durable cement, right, now we're back to our termites, and these particular mounds found in Brazil between 400 and 4,000 years old, so they've got some staying power. Ideally, right, we would like to bring that in and build a more durable home. Not only do we want to get a place for someone to live, it'd be nice if it lasted, and so we can just keep reusing that same house. So a few things up here that I'll quickly mention. To be able to 3D print, we need to be on this line right here for compression strength. So this is the number of layers. You can imagine if I'm coming across and I'm laying down my wall, I've got a weight that's coming down. So we need some particular properties from a geopolymer cement before we're going to be able to build this thing. So we need it to be able to go through the printer, all right? We need it to not have any of the slump. We need it to hold the next layer. And then when we get done, we want it to be strong. So what we have right now is a compressive strength. We're getting about 27 megapascals compared to ordinary Portland. That's about 13 megapascals, right? With the geopolymer cement, you get about a 40% reduction in CO2 in making the mix for that cement over ordinary Portland cement, which is what we see all over the place. But we need to continue to improve those properties. So that's where, if we take a look at what the termite is doing chemically, all right, this is a mucopolysaccharide, and that's in their spit with an enzyme. So they move their rocks around, they move their sand around, they build their walls, and as they deposit it, they're putting the cement with it, the thing that's sticking it all together. And then that cellulase enzyme is going to break it down, and it's going to hold the pieces in place. So briefly, because I'm out of time, we have tried a similar structure. All right, so this is what we've got in nature. We've tried sucrose. It actually decreased our compressive strength. We have tried sawdust, which is cellulose and lignin, and we kept the strength. We also didn't get any improvement in toughness. We're looking for some flex strength. So from here, we'll try, these are two other, again, they're going to be similar in structure to this. All right, the glucosaminoglycans are this. That's where we're going next. And the dream is that we're going to clean up the waste that we've been cranking out for 100 years. We're going to get a quick mix that you guys can use around the home, and we're going to get a 3D printing mix. So I will leave it at that. And say thank you to the USDA for funding us. Thank you to Giles County for supporting us. And if anyone is looking, for some chemistry, that's why we're here. We're trying to find matches with everyone that's doing the biomimicry work in all different disciplines. Thank you.